Can someone try to log into the Zoom and see if you can actually see the screen, or it's because there are two extended screens. Can someone try to log into the Zoom and see if it works? It works? Yeah. Okay. Miranda, can you see the slides?
Yeah, I can see your screen.
Okay. All right. Okay. Let's start. Well, so welcome to the semester. So I know like you guys when you guys enroll, hey Alex. So when you guys are enrolling this class, you probably see the title machine learning for embedded system. That's kind of like very like 1 year ago, like when they asked me for a title for this class. So but in this class, I'm going to talk a lot about not just embedded system. It's more just about efficient deep learning in general. So I'm going to go over like the content really quick. Miranda, can you see the website as well?
Yeah, I think so. It says like recent announcements.
Okay, yeah, great. All right, so this is kind of the rough content I'm going to cover for this class. Um, First, it's about like 13 weeks because I'm taking off um, I think it's next Monday. It's Martin Luther King. Then we have spring break, so we have roughly 13 weeks to go over this whole class. So we have I'm going to talk about the basics of deep learning. So if you are here. So I assume you have at least have some basic, taken some, deep learning class one way or the other. How many of you already have at least taken one kind of basic deep learning class? Or you should at least have some basic knowledge of all these like deep neural networks, right? So in today's class, I'm going to, just give an overview introduction of this class. I'm going to talk about the basics of deep learning. And then like I'm going to go over mostly like model compression techniques, including pruning, quantization, neural architecture search. And I'm also going to talk about distillation and the TinyML. Basically, it's more about how to fit the large model into smaller devices. I'm also going to talk about, attention transformer and then large language models. So it's not just, embedded system. But also like I'm going to talk about all these optimization techniques for large language models, deployment, vision transformer. I'm also going to talk about generative models, including like GAN-based or diffusion-based image and video generation. And I'm going to go over the basic algorithms as well as all these optimization techniques, trying to make them more efficient. Okay, so that's kind of give you a general sense of what kind of networks we are going to cover for this class. I'm also going to talk about distributed training, and then like on-device training, how do you do tuning, fine-tuning on the device. I'm also Finally, I'm going to talk about some hardware accelerator PIM kind of more related to hardware design kind of content. So that's kind of the main topics I'm going to cover for this class. And I may add or drop some contents based on our progress. So I'm planning to have about 5 labs plus a final project. There's so most of the homeworks will be in the form of the labs because the end of the day, the most important thing is that you know how to do it, right? How to code the network, how to train the network. So the final project will be like in group projects. So you are going to propose your own project. You are going to discuss with me, and you probably like. So I'm planning to. So you guys are going to propose your final project idea around week 9. So by that time, you should already have a very good, at least like very good understanding of most of basic networks efficient techniques. So you are going to propose something that it's probably related to your interest, related to your research. Okay, so that's kind of the main, the big, very, very big picture of what's going to be covered in this class. Let me. Well, now that we have, you already have a general idea of what's going to be covered. So let's start today's lecture. One sec. Okay. All right. So a lot of topics we are going to go over about like model compression and efficient AI. But why? Like so this first slides give you the reason that you need to take this class. So the x-axis is the year, y-axis is the parameter, the model size. We can see that the yellow line shows all these accelerator memory from TPU v2 to 800. Now we have, of course, we have a H100 and B300. But on the other hand, if you look at the model size, you can also see from the very beginning for the transformer to GPT and now to this MT-NLG, while GPT-3 and to this, which now has like 530 billion parameters. And you can see like this is a huge gap. But like before I move to the next slide, I want you to think about, well, is this, when I draw like a gap over here, what exactly does it mean? So does here it says like the 800 has like 80 gigabytes of memory for the accelerator for the GPU, right? But the parameter is for this model, the parameter is 530 billion parameters. And let's assume all these models are using like 16-bit floating point parameters. So how large is actually this 530 billion parameters in terms of storage? So 530, if it's a 16 floating point number, so the 16-bit floating point number, each parameter takes how many bytes? 16 bit. Oh, okay. So let's say it's a 32-bit. If it's a 32-bit, then it's going to be 4 bytes, right? If it's 16-bit, it's going to be 2 bytes. Now we have a 530 billion parameters. What's the parameter size we need to store for this model? Alex? A trillion bytes. I'm sorry? A trillion bytes. So 1 terabytes, right? So 1 trillion, 1 terabytes. So 530 bytes times 2, right? So if you think about that, that's how much memory you needed to actually store the parameter. So it's 1 terabytes of memory. And we only, for the GPU, we only have 80 gigabytes. So apparently we can't fit everything into the GPU memory. But we all learned computer architecture. We know that we don't have to store everything in the GPU memory to run the model, right? So we can do it. Yes. Take batches. We don't need to process we don't need to store the whole model into the memory, right? So so this MTNLG model, I believe it has a 105 layers. So let's say like it has 100 layers. Okay. So if we have 100 layers, apparently we don't need to store like the parameters for the whole 100 layers into this, right? So we only need to, let's say like we take batch, we take layers, okay? So we just process the whole model layer by layer, and there are 100 layers. So tell me like for each layer, how large we need to store the parameter for one layer. Yes. So around 10 gigabytes of memory, we need that much, right? So we need and then like we have 80 gigabytes, and we only need 10 gigabytes for each layer. It sounds perfect because now what we can do is just 10 gigabytes. We process the input, and then like we let the intermediate results stay in the GPU, and we grab the parameter for the second layer to the GPU, right? And then we just keep doing this. That sounds perfect, but what's the problem? Why that is not efficient? Why that it's not efficient? Yes.
So like loading data is gonna take a lot of time.
So loading data is gonna take a lot of time. So just to give you guys a sense of like what we are looking at. If you are moving data from GPU core to GPU within the GPU, the bandwidth about 1,000 gigabytes per second. Okay, 1,000 giga, so that's 1 tera ish per second within the GPU. But if you want to move the data from the CPU to the GPU, so from the CPU memory to the GPU memory, usually it's connected by PCIe Express link, right? And do you know what's the bandwidth for a PCIe link? Anyone take a guess? Yes.
20 gigabytes per second.
That's close. So usually it's like, let's say 32 to 64 gigabytes right now. Okay, so 32 to 64 gigabytes for 32 to 64 gigabytes per second. But then like if you think about it, we only need to transfer 10 gigabytes for each layer. We still think like, that's not such a big problem, right? So why that's not efficient? Yes.
That it has to do them one at a time, so that they have to wait for the next one or do the previous one.
What one at a
So
time?
there's one layer has to wait for one.
Well, sure, that's fine because then like if you think about it, like for the output, for you to have the output, then like you need a 10 gigabytes of transfer, right? So that's like 1/3. Let's say like we have the fastest PCIe, then that's give you 64 gigabytes per second, right? So 10 gigabytes for one layer, so 1/6 second you can process one layer. Compare with the data movement, the computation actually is quite fast. So let's say the bottleneck is just the data movement. So 1/6 per second for one layer, and we have 100 layers, right? So that's like 100 divided by 6 seconds for one output. Why is that a problem? So 100 over 6, that's how many seconds? Like 15, 16 seconds, right? 15, 16 seconds for one output. That's not too bad, right? For the large language model to generate one output for you. So what's the catch? So I'm trying to, this is important because this calculation is important because I want you to understand why we are even doing all these, pruning, quantization, why it's important. If we were not doing this, how slow it can be. 15 seconds is not too bad. Yes.
So what's the output? Is it like, if we're talking about an LLM, is it just one word or is it sentence?
So very good. So that's the catch. So when I say like when we have 15 seconds to generate one output, that's one token. And in a lot of large language model nowadays, we know like you do this autoregressive. Do you know what's autoregressive? So let's say like I have a black cat. Okay. So when you enter like the starting token, so it gives you this I, right? And then like once you have the I and the starting token, that's the two token you already have. So you are going to feed these two tokens to the model and to generate the second token, half. Okay. And that's for every token, for every word you are generating, you need to run this whole model one time. So basically for each word you have, you need 15 seconds. Okay. Now I have a black cat. That's how many words? I have a black cat. That's 5 words. And that takes like 5 words takes 75 seconds, which is over 1 minute to generate 5 words. See, so that's the problem. So when you are doing this autoregressive, basically, once you have generated one new word, you are going to use that new word as the input to feed into the model to generate the next token. And then once you have the first, the third token, you are going to feed the first 3 token to the model to generate the fourth. Does that make sense? So that way, if you want like five tokens, you're gonna like need 75 seconds to do this. Okay, so that's just not acceptable, right? So that's the whole reason that this is not efficient at all, and there's a huge gap in this. If we were able to fit the whole model, somehow we prune it, we quantize it, we distill the model. If we can fit everything, the whole model into this GPU, we don't need all these data transfer at all. Does that make sense? So the saving is huge. And like when it comes to server, to companies like Google and OpenAI, and that time equals money, right? So because that's the time that it takes to serve your request. Okay, so that's why it's so important. All right, so model compression. So by now you probably have heard about model compression one way or the other. So there are different ways. They have usually we have this pruning. We can prune the synapses. We can prune the neurons. We can do quantization. Quantization means that for every parameter, if it were a 32-bit floating point number, now we can replace it with just a 8-bit integer or even 4-bit integer. So by doing that, like we are saving the storage and the computation power a lot, right? So those are pruning and quantization are the most traditional, typical, have been well studied in the past decade. Distillation means that like we have a teacher model and teaches a smaller student model. So when we are doing the pruning, it's always a trade-off between the accuracy and the efficiency. So you always sacrifice some of the accuracy. It just depends on how much accuracy you are willing to sacrifice to gain the performance or the efficiency improvement. So this is the kind of the number of publications. Everything's the first paper is a very interesting name, optimal brain damage. So it says like how you are pruning the synapses and neurons to have this brain damage, but it's optimal. So that like you maintain the accuracy while make the model smaller. Then like I think it's about 10 years, about over 10 years ago, then we still see a huge jump in the number of research in terms of how to do the efficient AI. It's everywhere. The most important applications are vision and the language model are the 2 most important applications. But now also like we have more and more multi-model, multimodality models. Means that like we have this both vision, language, or even other type of sensors that feed into the model to do the decision making. So, but they are computationally costly, and how to make them lightweighted and fast is the core of this class. So next I'm going to talk about vision, language, and the multimodality models. Go over some of the most common models now nowadays we see. And also I'm going to briefly talk about the optimizations we are able to do nowadays. So first for vision. Deep learning for image classification has been the most common, the best, well-studied the application. So image classification, ImageNet was kind of the first one that kind of achieved this superhuman performance. So on ImageNet, this top 5 error for human is about 5%. So what top 5 error rate, it means that if you ask someone to predict, like, what does this image look like, and you give me 5 options, what are the top 5 most likely output? This looks like a mushroom, right? Or like as you say like the most likely is a mushroom. It might be a small house. It might be a toy, right? So that's all these possibilities. As long as the correct answer is in the top 5 guesses, then we think you are correct. So that's what top 5 error means. So for human, it's actually the error rate is 5%. You still like make 5% of error, even we allow you to guess 5 times basically. You still like for this ImageNet, you still make 5% of errors, and you can see that by 2017, the deep models, they already can achieve 2.3, which is much better than human being. But all these accuracy, they come with cost, right? They come with prices. If you look at the right-hand side of this figure, the x-axis shows the max, the multiplication accumulation operations, and the y-axis shows the accuracy. If you just look at the right-hand side, most of the models are not compressed, and you can see that like if you for this NASNet A, it's about like 4.5 billion max multiplication accumulation. Okay, with all this left-hand side, most of the models are compressed and optimized the models, and especially you can see that for this once for all model, you can kind of like achieve really good performance over around 80% of accuracy with only less than 1 billion max. Okay, because 1 max has 2 operations, 1 multiplication and accumulation. Okay, so 1 max has 2 operations. So you can see that. So essentially, you can reduce the computation about 10 times while maintain similar performance. Of course, it's you still have like 1%-ish accuracy drop, but the computation safe is huge, right? So that's kind of thing that we are looking at. Segmentation. So this actually was released, I forgot it was last year or 2 years ago, this segment everything by Meta. So basically, this model, you can just click the object and it can just segment the object for you, right? And I think you can still like access this model from segmentanything.com. It's released by Meta, and they can automatically segment everything in a image, basically. The original segment anything based on vision transformer can process about 12 images per second. Okay, and you can see for all these slides, you can see like there's a red dot. So what it shows that like if you click on this part, it's going to segment this whole object. And basically here, if you click on the shirt, it's going to segment this whole shirt. Right? You can see the red dot over here, right? So here is the floor. This is the floor. And if you like this efficient VIT was published in 2023, so can achieve pretty much the same performance you can see here. I don't even know what is this. Like this part. Anyways, this is shirt, the floor. So the efficient VIT can improve the efficiency by like can process 842 images per second. So again, that's a huge jump, right? With pretty much the same performance. This is also a demonstration of the efficient VID. This is a road. I think this is a hat, and that's the car. From discriminative model to generative model. So we know like when first generative model came out, most of the image generation are based on generative adversarial models, networks again. Later, we kind of gradually start to use diffusion. So this just gives you the example how you are, this is actually diffusion model. So how this teddy bear mixing sparkling chemicals as mad scientists, a bowl of soup as planet in the universe as a 1960 poster, a photo of an astronaut riding a horse on Mars. Okay, so but training the diffusion model is expensive. Training the stable diffusion costs about 600K to train the model. So that's like 256 800s and 150K hours to train this model. And later in this class, we're also going to talk about how does diffusion work and how do we optimize this diffusion, both the training and the inference process. So this is a GAN-based generation. I think, let me see. So let's look at this chart first. So basically this one, the x-axis shows different models. The y-axis shows different max. So the red ones are the model that's after compression. So you can see that the computation can be compressed like 20 times to achieve similar performance or even better. So it's interesting, like, or even better performance. So let's look at this example. This is the original model, the CycleGAN. So FID is this image distance. Basically, we are trying to, the FID number, basically we are trying to calculate the distance between the generated image with the original, the real image. So apparently the distance is the smaller, the better. The smaller the distance is, it means that the more similar your generated image to the original image. Does that make sense? So this is original CycleGAN. And if you look at this one, this the same zebra generation. So you can see that it's compressed about more than 20 times. And the image distance actually is just slightly increased, right? So remember, like for the FID, the image distance, the smaller, the better. But if you look at this compression algorithm, we actually compress the model a little bit over 10 times, but actually the FID got to 26.6. So the image is more realistic with less computation power. And then like we also have this this any cost again published in CVPR 21. So like if you guys are interested in any of these techniques, I always list the reference here so you can look it up and you can look at the technical details. I might not have the time to cover like every paper I mentioned here, but I'm going to mention like the most core papers. For this any cost again, you can pretty much run this on a laptop and can have all these options and basically we can we can reduce the computation power while maintaining the same generative power. What is this? So this achieves interactive image synthesis and editing on laptop. You can see that we can reduce the computation budget by this. And again, if you translate that to the cost, that's what most of the cloud service provider, all these larger model service provider cares, right? So that's 5 times reduction of the cost. The 5 times, not 5%. And this is another paper efficient spatial sparse inference for conditional GAN and the diffusion model. So this one is the in painting. So what that means is that I give you this image and do something to this image. So this one says like, well, based on this image, basically draw a horse on the grassland, and can do that. Stable diffusion, it's going to take 369 milliseconds to do this, and that's how many operations you need. And this paper basically says they can reduce the computation by almost, well, over 3 times, and the time also is reduced like almost 4 times. This is like more translational from a sketchy to a realistic image. So it says like the prompt is fantasy beach landscape trending on art station, so that kind of thing. Stable diffusion needs 369 milliseconds, and this paper can achieve like almost 5 times improvement in terms of generation speed. Okay, so it's faster and cheap. What else can you ask for, right? So this is a faster composer paper. It's more focusing on multi object generation. So here you give 2 images, a man and a man sitting in a park. So that's kind of the results. It can like correctly pick the 2 inputs and into one single. And this one is also 2 subjects. This is Fei Fei Li, a woman riding a horse. It can correctly do this. Fast composer, they can have some really interesting examples. And not just 2D image generation, also 3D model generation. So diffusion can help you generate all these 3D models. This is Objectverse. You can actually check this out. And then like we have video generation, right? Not just 2D image, 3D model, but also like video generation. This Objectverse also has some examples. So now like we already see on a lot of social media, you already see a lot of AI generated videos nowadays. And not just 2D vision, but also 3D vision especially for autonomous driving. So for autonomous driving, either you are using just a plain camera to take a 2D image, or you can have this LiDAR to capture the 3D point cloud, right? So basically it's LiDAR hitting the objects and to get the reflection back, and then you plot all these dots to construct this 3D image. And also like we can Waymo is pretty much using this, and deep learning helps the machine to perceive the surrounding 3D environment. So that's most of the common applications you have already seen for the vision applications. So what about language models? Apparently, like all these ChatGPT, Gemini thing. So ChatGPT model produces human-like text based on past conversation, and also like code generation, right? So I think this slide was a little bit outdated already. So GitHub Copilot can help you, and now I think Cloud is doing great, and I think like PIS student has free access to the Cloud subscription, right? So you guys can try this out to help you do code. So one of my students graduate went to Facebook, Meta, and they in a lot of all these companies, they are already doing all these vibe coding. So basically, just describe what you want to do, and automatically generate the code for you. And your job now becomes, well, instead of like writing all this code, now you need to kind of verify the code that it generates is well structured, it's correct. So it's kind of the role shifting is very interesting. But for a lot of basic functions now, like all these generative models can already give very high quality code, especially if you know how to break a big task into smaller tasks and ask the model to generate all these smaller tasks and just pieces them together by yourself. And that actually improved the productivity definitely a lot. And it's already, happening. Translation. So neural machine translation, and that's another very common application. And this one basically says like this how they are trying to use the transformer to do the language translation. And from here, like the x-axis is all these different compression methods, and this is the model size. So you can see that like by doing quantization and pruning, quantize to 8-bit, you can reduce the model size quite a bit. And the blue, the blue and the blue line. The blue is the metrics to measure like the semantic similarity between the original text and the translated text. You can see that like we only have, after you compress the model by almost 20 times, you only have a very small drop in terms of the blue score. And large language model shows emergent behavior, zero or few shot learning. What that means is that for this model, like you don't need to specifically train this model, because the large language model it's a generative model, right? So it's not supposed to do the translation, because all it knows is how to generate the next token. That's how the model was trained. But now, like if you just give a 0-shot prompt, it can actually just immediately start to do the translation for you. So the task description, translate English to French and cheese, and that will give you the French cheese. And some tasks you can also do this so-called a few-shot learning. So just give a couple of examples to the model, and it will learn how to do the translation. So in this figure, the y-axis shows the accuracy, improve. So you can see that with few-shot learning, just give a couple of examples to teach the model. The performance increases, but also like on the x-axis, you can see the parameter size increasing. So then another thing is this chain of thought. So it's the reasoning capability. So now, like if you notice when you are now for most of the services that you are using, either Gemini or ChatGPT, when you are trying to ask a question, actually you can see that it actually gives you shows you like what it's doing in this step, and that's pretty much the reasoning part. So instead of just directly give you the result that you want, it actually breaks this whole inference process, whole generative process into multiple steps, and that actually improves the accuracy. So that's and give you this example here. So this one says, well, the model, the inputs is that says like so this is a few-shot learning prompt. You are teaching the model says, oh, Roger has 5 tennis balls. Okay, he buys 2 more cans of tennis ball, and each one has 3. So how many tennis balls does he have now? So the answer is 11. So that's 2 times 3 plus 5, right? But you just give this says like the answer is 11. And then you ask, well, the cafeteria has 26 apples. They use 20. Buy 6 more. How many apples do they have? And they give you the right answer, which is 27. Okay. But if you are changing the way that you are asking it. So this is a so-called like this string of thoughts. So you are pretty much teaching it how to go through this whole logical process. Says, well, I have this, 5 tennis balls. And in the answer, instead of just telling the model says the answer is 11, you are telling this, Roger started with 5 balls and 2 cans of 3 tennis balls, each is 6 tennis balls. And 5 plus 6 is 11. The answer is 11. So once you are teaching the model how you get the answer, it actually can mimic your process and give you the correct answer. So once you do that, you can see that the model outputs the cafeteria 26, they used the 20, so they have 3, and now they bought 6 more. Now 3 plus 6 is 9. So that gives you the correct answer 9. Okay, so that's so-called like the train of thoughts. There's a reasoning process, and this really helps not just improve the accuracy, but also this one give you this kind of a break this big task into multiple steps, give you more. If something's wrong, you can actually trace back to know more about what's wrong, right? So especially in a lot of nowadays in like autonomous driving or in robotics, so kind of people want to know, like, you know, when the robot does something or the car does something, you want to know what is, well, in which step it makes the mistake, right? You want to break this into multiple steps to know which step give you the error. This one is the testing of different models on middle school math word problems. And you can see that the black line is the standard prompting, just give the question, okay? And the blue line is the with the train of thought prompting. So you give a couple of examples of how you come up with the answer. You can see that train of thought actually improved the score significantly. And of course, like, then you may ask, like, what's the catch here? So train of thoughts actually is going to take longer to do the inference. So you are paying the time and the energy to do the computation. So how to make, so what that means is that, like, let's say like if you have a robot and you want to generate some action, and if you want to do, basically it's already very slow, right? So if you want to do the chain of thought, you want it to be more accurate, more explainable, but now like makes them even slower. So how to efficiently do the reasoning is also like a really big research area nowadays. So that comes back to the first image. Now I hope I already convinced you that, you know, efficient AI is very important itself. It's a huge topic, and there are companies have, you know, monetary benefits interested in doing this, because that literally reduces their costs of running the service. So this is a for this attention. So we haven't really formally introduced what is attention, but just that's I'm going to give you the detailed explanation later. But now I'll just give you like a very high level kind of explanation. So most of the large language model nowadays are based on attention. The attention architecture. So Google has this attention is all you need paper. So what this paper, this sparse attention paper says basically how it's pruning both the tokens and the attention heads on the fly. So like, for example, as a visual treat, the film is almost perfect, okay? And then like, when you are running this, you know, this model, it automatically says, oh, when I see this, I only need it, after I run this first layer, actually I find out I only need it as treat, film perfect, only needed this 4 tokens to actually do the task. Okay, for example, like I'm just classify the sentiment if it's positive or negative. So I gradually just find out I only need 4. And then like after layer 2, I find out I only need 2, actually film perfect. And that's the only 2 words I need to get the sentiment. Okay, so in this way, for each layer, you process less and less computation. But how? What's the main idea? So main idea is here. This is the attention map. So you can see that like this is the kind of a well, this sentence says, I bet the video game is a lot more fun than the film. Okay, the y-axis is still the same, and this is called self-attention. So what attention means is that basically says, well, on here it says this is a query, this is a key. So basically it says, well, the word I should be associated, or which word should I pay attention more? Which word is more related to this query? So for example, the I says like it's more related to this lot, okay, and also fun, okay. And video is very related to this game. Well, that's apparent, right? Game is related to video because they always come together, like shows up together, right? So that's somehow they just capture that relationship and give you this attention map. Okay, so that's for now. Let's just think about each cell of this attention map shows the importance or the tie, the relationship between these two words. Okay, so what this paper does is that well, for once you calculate this attention map, and then for all the column, we adding all the attention value together for this whole column to get one value. Here it's 1, for example. Okay, and then like each column is going to have this accumulated attention number here. So what that accumulative number means is that, well, for example, for video, for this word video, like how many of other words in this whole sentence actually pay attention to me, right? So the higher the number, it means that more words in this whole sentence pay attention to me, means that I'm important. Does that make sense? So I use this mechanism to indicate I'm the important word in this whole sentence. Okay, so now by doing that, you can see that, well, the bet has 1, this game is 1.7, right? And this is a lot. What is this? A lot. It's 1.8. And then like, we can see some other tokens like I, not important. This the. So see, so like this kind of words are very generic. It doesn't carry any meaning on it. It automatically finds out they are not important in terms of how do you do the sentiment classification. Does that make sense? So in this way, therefore, after the first layer, I have this whole kind of the cumulative value. Then like I'm going to delete all those not important tokens and only pass the important tokens into the second layer. Does that make sense? And then when I'm doing the second layer, I'm going to do this whole attention map again, but not just doing the attention map for this particular layer. I'm also going to add this accumulated value to the value I got from the previous layer. So this is kind of they accumulate the attention importance from previous layer as well. Okay, for each layer, I accumulate all the attention that paying to me, but also I'm going to accumulate to the attention I got from the previous layer. Okay, so by doing this, I'm going to prune all these layers and tokens. I'm sorry, prune the tokens and the heads, not the layers. The attention heads and the tokens, and then like gradually, I just need to know I only needed 2 tokens to do the sentiment classification. Okay, so that's kind of so that already gives you a kind of a general idea of how we are making the model efficient as well as maintain the accuracy, right? So that could give you a sense of it. So multi-model. So next, let's talk about multimodality. Multimodality means that like, well, for example, like the vision and the language, how can we process them simultaneously, right? Not just a single modality. So this LLaVA achieves this general purpose vision. So most of the large language model nowadays can process vision language simultaneously. So I've been using Gemini a lot. You just take a picture and ask a question. Give you a lot of like really good suggestions. Well, do you know who drew this painting? So basically now the prompt input, including the prompt plus the image, right? And you need to kind of understand each other. Like, well, I need to understand like, this is the painting I'm referring to. And then I need to actually to extract like what is inside of the painting. And then with that painting information, I need to like, generating all these texts. Okay, so that says a woman commonly believed to be Mona Lisa, the famous artwork by Leonardo da Vinci. And this one actually give you a very this AWQ is a very famous quantization paper. It's trying to quantize all these large language models to 4 bits. So instead of using 16 or 32-bit floating point number, it's trying to quantize both the weight and the activation to 4-bit integer. That's a lot, from 32-bit to 4-bit. Okay, and we are going to talk about like how it's doing it while maintaining all this accuracy. So so you can see that this is the original model. I'm sorry, never mind. So so these are 2 different model. Both of them are quantized to 4-bit. So this is AWQ, this is RTN. I believe this is another paper. So you can see that like this AWQ actually can generate more useful information about this. So this is also like I see this on social media actually. This chicken nuggets with a world map, right? So it can actually understand the humor of this. So that's like the image is light-hearted and humorous take on the concept of looking at the picture of the Earth from the space. But actually, it's a plate of fried food, especially chicken nuggets. It's presented with the caption, "Sometimes I look at a picture of the Earth from space and marvel at how beautiful it all is." The playful combination of a food item and Earth-related context creates a fun and entertaining visual, right? So that's just give you very impressive. This one is more like a robotic transformer controls a robot based on the language instruction. So the robot needs to look at the camera with the camera and also like follow your instructions. So the vision and the language model process both inputs together and do this. And this is like a very active research area right now, how to make this more efficient. Right now, if you think about right now, most of the large language model are still running on the cloud. So when you are giving the instruction to the robot, it's taking the picture, it's taking your command, sending to the cloud and process it. So the connection just takes time, right? And also, if you don't have the connection, then it's useless. But for this kind of platform, the computation power is not a lot. So how to run a vision language model on this kind of small devices is a very active area. And not just like for this one, it's probably like the action the robot can do actually is also limited. For example, probably just just go to the drawer, just move. But like if you want like a fully automated robot with all these actions to grab, to do all that, so like there are a lot of action generation also need to be done. So those are all. Every new task comes with a price, and like our goal is how to optimize the model to make like we want to pay the less with the most gain, right? So that's the whole efficiency. That's the whole like the efficiency thing we want to do, and that's the whole thing this class is about. Deep learning for games, AlphaGo is based on reinforcement learning. So for each game, AlphaGo needs to the electricity bill is about $3,000. And this is the protein discovery, and we know like Google, the guy from Google won the Nobel Prize for doing all these, right? So so the protein discovery basically says I want to predict the 3D shape of the protein based on a 1D amino acid structure. So I'll give you just 1D amino acid structure. I want to predict the 3D protein. So traditionally, without the alpha, why this is significant? Why the AlphaFold is significant? Because traditionally, if you want to capture the 3D structure of a protein for one protein, usually takes months to years. Now it's let me see. I think I have to. Do I have the number? But now like it's pretty much to predict all these, you just need a couple of hours, like all the proteins. So basically, you used to like thousands of proteins structures, like a couple of hours. like which means that like traditionally we probably need 100 years of measurement and expensive investment in terms of all the equipment. Now just a couple of hours. So that's why it's significant. And why like predicting the protein structure is important, because in a lot of antivirus medicine development, the pharmaceutical development, you need to know that the structure of the protein to know how they are infecting the cells and all that. And so that's why this is so important. 3 pillars of deep learning: algorithm, hardware, and the data. So hardware. First, let me talk about the hardware. So computer architecture development has been, also like along this past decade has been evolving a lot. So starting from, especially to support all these compression methods. So we know that like due to model pruning and quantization, we have, from dense architecture to sparse architecture, from floating point 32 numbers, all the way to integer 8 to even, as I mentioned, like to integer 4. So that in order to do those computations efficiently, you need a hardware support. And you can see that like if you just look at the transistor increase, the slope is this. But if you look at the integer 8, this is a teraops per second. The increased slope is much significant, quicker, much faster. So that has a lot of not just it's not this increase not just come from the increasing of the transistors, the scaling, all that, but also comes with the innovation in architecture design. And for this figure actually shows the for every generation of technology node from 65 nanometer to all the way to 5 nanometer. This is the breakdown of the cost of like migrating from one technology node to the next technology node. For example, let's say like from 10 nanosecond for 10 nanosecond 10 nanometer technology node, for when you are developing this new generation of chips architecture, the CPU, GPU, and then like all this software, and that's how much money usually you need to invest to become a mature ecosystem. And you can see that like once you approach like 5 nanometer, everything just jumps because everything becomes harder. Apparently, to do the software to more efficiently utilize all these transistors you have, all these architecture innovations you have, also like software investment also is a significant part of this whole ecosystem. And that's why like in this lecture, majority of our folks, we are going to talk about how we are going to optimize the software to utilize all these transistors, all these architecture innovations we have. This one shows the cloud AI hardware evolvement. So this is four different generations from P100 to H100. This figure shows across these 4 different platforms, the increase of the floating point 16 performance, the teraops per second. So you can see that jump. This is the memory bandwidth. Okay, so that's what I said. Like for within the GPU, the memory bandwidth is about 3,000 gigabytes per second. That's for like this H100. This is the power jump, and this is the memory jump. For 800, the memory was about 80 gigabytes. And this is the comparison for different edge hardware. So this is for the Qualcomm DSP processor. So DSP processor were used for signal processing applications right now. But because if you think about for signal processing, all this FFT, this IR, the FIR, they're very similar. They are pretty much just matrix multiplication, right? So that's why like it's also like used extensively in mobile platforms for all these AI applications. You can see that also the performance increase, the power is kind of capped. What that means is that basically we are with the same power envelope, we are constantly improving the performance. So that's quite something. And the memory kind of limit to 16 gigabytes now. So this one shows different generations of Apple, this neural engine. So from A11 to A16, now the performance is about 16 tera operations per second. So I forgot the accuracy. I forgot the accuracy for this Apple neural engine. I forgot it's a floating point. How many bits of floating point? But you can also see the performance curve. Kind of interesting that you drop the watts, but come back again, and that's the memory cap. So this is for the Jetson, NVIDIA Jetson. It's a completed system. So you can see that compare with Apple and this Qualcomm engine, the Jetson has a significantly, well, of course it's bigger, that's its own fan. So, but it gives you this different generations, the performance increases dramatically, while the power also increases and the memory also increases. This is the TPU. I don't have the latest TPU information, but the first generation of the mobile TPU, the tensor processing unit, give you this about 4 tera tops at 2 watts and 8 gigabytes. And if you can compare like across different platforms, kind of also give you a sense of what kind of hardware we are dealing with nowadays. This is an FPGA-based accelerator. I know some of you might be doing research on FPGA, but if you look at this, to achieve similarly like this, let's say 4 tops, let's go back to this TPU with 4 tops, 4 tera operations per second. We are capped at 2 watts, but apparently FPGA takes significantly more power to do this, achieve this 4 tops. The memory is also bigger. Then microcontroller. Also this KCU can achieve about 4 tops with larger power and the memory. So edge AI devices still have a huge gap to cloud processors, apparently. So we can give you this cross different platform comparison, the memory, the storage. So now we kind of talked about all the algorithms, all the hardware. What about the data? So now this is kind of the ecosystem. So we have a lot of computation, a lot of data, a lot of engineers, and the goal of our class and our research is about to shrinking everything. We want less computation so that we have less carbon emission. So if you think about it, at the end of the day, once we all have all this data, this computation power, now power gradually becomes the capping factor here. Because now for every year, all these AI services combined, the power they are consuming is about 2 New Yorks every year. 2 New York City. So that with that skill, that's why people start to talk about building small fusion nuclear reactors for data centers for all these servers, or you can do that with the satellite. You want to harvest the energy from the solar power on the orbits to support all this because eventually this is about the cost, right? So to get that much of energy to run all these inferences and training, business wise, it's about how to make them cheaper, more sustainable. We want less data, fewer engineers. Okay, so that's 7 to 1 hour. So that's for the first lecture. Any questions before we take a break? Okay, so next let's take a let's say 15 minutes break. Let's come back at 7:20 and we'll start the next lecture. 你说
那些论文上面拔了。然后
你说那个 CPS 那边吗？
对，其实